Hi everyone, my name is Chen Hao and today I'll be talking about motivating the Legendre transform. So let's start off by talking about different representations of the same function. Given a function f of x, if I give you the function f of x, can you return me a representation of it? By representation, I mean can you return me enough information encoded in a different way such that I can reconstruct the function f of x given some procedure. Some familiar examples, I believe, would be the Fourier transform, right? It's basically the function f of x but in momentum space or frequency space. If you give me the Fourier transform function f of k, f tilde of k, I can perform an inverse Fourier transform to get back the original function f of x. In circuit analysis, specifically LCR circuits, right, the Laplace transform is also very useful. If you have a differential equation, you can often transform the solution function into a function that into a Laplace transform function that takes in a complex parameter s, and roughly speaking, s is made out of the frequency and the decay components. So in some sense, Fourier is a specific case of Laplace. This turns the algebraic equation, this turns the differential equation into an algebraic equation, which you can solve more easily. Now today we'll be talking about another representation of the function, which is known as the Legendre representation, and this will correspond to the Legendre transform. So the Legendre transform of a function takes in a parameter p, which is the slope of a function, the derivative of a function. Now we require that the function f be convex, because if the function f wasn't convex, then there are multiple points on the function that give you the same slope. So that wouldn't be good for constructing a single valued function. Okay, so let's elaborate a bit more on convexity, right? If f is a convex function, that means that df over dx is monotonic. The derivative is monotonic, and the second derivative is positive. In some cases, they say it's negative, but we'll stick to the convention saying that convex is positive and concave is negative. So if df dx is monotonic, then this function, which I rename as p, right, is invertible. If we denote this inverted function, this inverse function, x of p, what this means is that if p of x, right, is a function that takes in a value x, for example x1 over here, and returns a slope of the function at that point, then x of p will be the inverse, meaning that now I'm going to give you the slope that I want, and you're going to tell me the x value at which this slope occurs at. So in other words, right, in this example, if I've given this function f of x, and let's say I have the two red lines over here representing gradients -1 and +2 respectively, then if I give you a -1, I want you to return me x1, because that's the x value that gives me the slope of -1. Likewise, if I give you +2 into the function, x of +2 should be x2, according to the graph over here. Okay, so now the question is, is this x of p enough information to reconstruct the function f of x? Is this x of p a good representation of f of x? And turns out the answer is no, because one can check that if the function x of p returns me the x value at which the slope is that slope, then if I have the x of p alone, I could not have told the difference between two functions, f of x and f of x plus a, meaning that if I translate the function f of x, right, the graph, if I translate it upwards, right, we can see that the function x of p, given the slope, it returned me the same x value. This means that x of p cannot distinguish between functions that differ by a constant y amount. We're missing, in some sense, we're missing the y information. In fact, if we know a particular point that which a function passes through, we can reconstruct the entire function. But we're not given this information in x of p. So what can we attempt to do? Why not we try to return y of p instead? So if I take x of p and I pass it into the function f of x, right? Then now it corresponds to, I'm going to give you a gradient p, and you're going to tell me the y value at which it occurs at. Now, question is, is this enough information to reconstruct the function f of x? And turns out the answer is no again, because in the previous example, right, we can see that translating the function up by a constant amount doesn't change the x of p, But in this case, translating the function horizontally, it also doesn't change the y of p. In other words, two functions can give the same y function. We're missing the x information. So this makes us scratch our head, because if we cannot return the x information, cannot return the y information, then how do we reconstruct the function? Right? A function is defined by the set of x, y points that the graph passes through. And if we can only return one such information, then we definitely cannot find out the other one. But it turns out we missed an important fact over here, which is that when I ask you for a gradient p, right, that kind of relates the x and y in some sense, right? Namely, if I give you a gradient at a point, right, it kind of determines slightly to, it kind of determines the value of the function at its neighboring points. So we have, by returning only x or y, we have kind of thrown out the p information. So the motivation for Legendre transform is that we want to squeeze the information out of this p, which means that the expression we have would kind of involve p in some sense. So we're going to make use of the fact that a convex function is uniquely defined by its convex hull. And what is a convex hull? We define it as a collection of lines. So if we see this red function over here, f of x, right, the convex hull will be all the black lines that are tangent to the red function, hugging the function in some sense. So how do we encode the entire convex hull? So one can see that if I return to this picture, one can see that if I give you the entire convex hull of the function, then I can reconstruct the function by taking the maximum of all the convex hulls, right? So I take all the lines, and for each x value, I calculate the height, the point, for each x value, I calculate what the y value of that line is, and I take the maximum among all the lines, and that's how I can reconstruct the original function f of x. But how do we specify the entire convex hull, right? Well, each line is defined by two numbers, the slope and the intersection with the y-intercept. A collection of lines will hence look like a pair of numbers, right? A pair of real numbers. It'll be an infinite set, but this infinite set will encode the entire convex hull. We can easily encode this entire infinite set into a function because of the fact that the gradients, each gradient only appears once. Because remember, a useful fact about convex functions is that the gradient, the derivative is monotonic. So each gradient only appears once. And that means that we can define a function c of m that takes in a gradient and returns the y-intercept of that line. And this turns out to be precisely negative of the Legendre transform. So we have negative over here simply because of the fact that we want the Legendre transform to be its own inverse, but that's a subtle fact. The key idea over here is to define this function c of m. So the Legendre transform is defined as the negative y-intercept of all the tangent lines, and one can define it as such. So y of p is the y-intercept. Y of p is the point y, the height of that point, and px, right, that would be if you take y of p minus px, that's the y-intercept of that tangent line, and we take the negative of it. So that's how we define f star. Or equivalently, we can define this as this thing using the maximum. So this basically looks through all the x values in the domain of f, and it selects out the maximum px minus f of x. So now, question is, what we're talking about just now was hypothetically if we had a convex, how we can reconstruct the function f of x by taking the maximum, right? But how do we do it in practice? And turns out the answer is that we perform a Legendre transform again. So in other words, Legendre transform of a function is itself. In fancy math language, they say that the Legendre transform is involutive, meaning you do it twice, you get back the same thing. It's its own inverse. And this is a mind-blowing fact, but we will unravel why this is so. So if we see the definition of the Legendre transform that we had over there, right, if we rearrange it, we get the following, where y of p was replaced with f of x, right, because that's just the definition of y of p. So if we take a look at this expression, it looks highly symmetric. We see that this, if we look at this expression and stare at it, if we can prove that f star of p is convex, then we can simply rearrange this expression into f of x equals to px minus f star of p, and that would be the Legendre transform of f star of p. So all that remains to do is to show that f star of p is a convex function. And to do so, we take, remember how we show a function is convex, we need to take the second derivative and show that it's always positive. So we take the first derivative and we get the following expression. So we get that the first derivative of the Legendre transform f star of p is actually x of p. So in some sense, previously, in some sense, f star of p definitely contains more information than x of p, because if you take the derivative, then you can recover x of p. So this is a bit of intuition about what f star of p really contains, right? It contains more information x of p by virtue of the fact that you take the derivative, you're throwing away the constant component that encodes the missing information you need to reconstruct the function f of x. So given this expression, if we then take the second derivative, we can see that because x of p is increasing with respect to p, because p of x itself is a monotonic function, we can easily see that second derivative is positive, and hence we have proven that f star of p is convex. So if we look at this expression now, right, we see that symmetric. We can move either f of x or f star of p onto the right hand side, and that would be the Legendre transform of whatever we moved over, and hence we have proven that the Legendre transform is involutive. So what is Legendre transform used for, right? In thermodynamics, we often see that we take differentials. We have exact differentials and inexact differentials. And often, these differentials encode the information of if you want to do a process at a constant temperature and at a constant at a constant pressure, right? Or maybe you want to do it at constant temperature and constant volume, or constant entropy and constant volume, or constant entropy and constant pressure, right? The differentials will encode that kind of information, and that is why we often use the Legendre transform, because the Legendre transform, right, by virtue of the fact that we have this px over here, we apply the product rule, it'll cancel out one of the things and give you other. So that allows us to swap the p dx into a x dp. And so that corresponds to processes at constant volume or constant pressure, or constant entropy and constant temperature. These are known as conjugate variables. I'll talk more about the thermodynamic Legendre transform in another video. Yeah. And where else is it used in physics? It's also used in Hamiltonian mechanics, where we often say that the Hamiltonian is the Legendre transform of Lagrangian. And this P, right, is the canonical momentum in Hamiltonian mechanics, and is defined as the partial derivative of Lagrangian with respect to Q dot. So that is actually precisely what we're seeing, right? We're taking the gradient with respect to a parameter in the function, and taking that as a parameter in the Legendre transform function. So there's actually a lot more fancy math about this when we study integral systems, right? Where we often talk about symplectic structures, or there's a line on the Wikipedia that says that the Legendre transform is actually a tautological one form on the manifold on which the dynamics is defined by. So the manifold will be the phase space, and the tangent space will be Q dot. The Q dot will live in the tangent space, Q will live in the manifold, and P will be a tautological. It will be a P will live in the cotangent space of the manifold. And basically, there's a lot of mathematical structure that goes into this Legendre transform. But that's for another video. So in thermodynamics, right? In thermodynamics, I won't go too much into detail because that's for another video. But basically, the reason we often use it in thermodynamics is because, as mentioned previously, we want to change variables into a set of variables where it's easier to describe processes at constant temperature, constant pressure, constant volume. And it is worth mentioning that often the Legendre transform is a purely mathematical construct, and we must investigate specific systems such as gases, in which the Legendre transform would pick up value, right? Pick up meaning, such as the useful work obtainable and so on. So yeah, that is all I have for today's video, and I hope you enjoyed it, and have a nice day.